So here's my notebook. I'm using the Cleveland Heart Disease dataset. It contains 297 patient records across 13 clinical and demographic features with a binary target variable indicating the presence or absence of heart disease. So there is mild imbalance in the data, as you'll see earlier. Uh, I'm gonna apply SMOTE onto this data set. Normally, if this was not a class assignment, I wouldn't even bother using SMOTE due to the mild imbalance. But yeah, we'll just move on. And I'm using five different classifiers: the KN, the SVC, the Gaussian NB, the decision tree classifier, and the logistic regression. And there's going to be a base model and a second model experiment with hyperparameters that are optimized via grid search. And this experiment is going to focus mainly on the recall and test F1 scores, um, which is targeted against on class one, those with a presence of heart disease, because we want to look at how well the model is able to predict class one and not flag false negatives. Okay. Okay. Just here, this just looks at whether or not the checking of the any missing or null data and the shape. There is no missing data. That's good. And the shape is 14 columns and 297 entries. Here, this is the first five rows, and it's a mix of categorical and continuous numeric data. Um, just right off the bat, there's going to be standard in this normalized data set due to the different ranges here. Here, just checking the data type. Um, Most of them is going to be int 64, except for old peak, which is going to be float 64. And if we take a look at the data a little closer, the thing that pops up to me the most, specifically for the continuous numeric data, um, many of them have really small standard deviations compared to their means, which tells me that there's not a lot of um, variance in the data set, and many of the data is nicely compact near its mean. It's not really so very spread out. Another thing I want to take a look at was cholesterol. You look at the mean and the minimum versus the max. Uh, the max is it's much higher than the mean and the minimum. So I'm going to try to check the outliers there. If you take a look down here, the threshold is 400, and there's only seems to be about four entries that meet that condition. So not a lot of outliers, and I don't think this is going to have much an effect on it. And so I'm not going to do anything about that. Here, the data cleaning. The only thing I did cleaning on here is encoding the non-binary categorical data, CP, REST, CG, slope, and thal here, or non-binary categorical. And secondly, I chose to keep the dummy columns, so I am able to visualize my data set. And with the heat map, let's take a little closer look at how all of these interact with each other. The trade-off there is that this introduces multicollinearity into my data set. But I'm not too worried about it because we're going to use a PCA transformation, which will um, collapse these um, these weak relationships. So yeah, we're gonna go on, and also if we take a look at the shape there, we went from 13 features to 23 features. So that is 9 additional dimensions that I just introduced into my um, data set there. And if you take a look at the heat map here, um, not a lot of strong relationships. Highest is between condition and CP3 with 0.51. And yeah, and everything is pretty, really, really weak relationships. And so here, if you look at the really, really weak relationship between thal 0 and thal 2 there. And that's part of the fact that I kept the dummy columns. And again, trade-off really minimal because we're using a PCA transformation later. So I'm not too worried about these really, really weak relationships at all. And so looking at the distribution between my two classes here, once again, if this was in a class assignment, I wouldn't even bother using Smote because due to the, a mild imbalance here. Um, yeah. And here I created a pair plot to kind of get a deeper look into what might go on here. As I was mentioning earlier about the standard deviation and the mean, a lot of these, at least for the top 7 here, the phallic, these classes are really, a lot of it's, pretty, normal distribution, really tightly clustered around its mean. Yeah, if you take a look here, and there's a lot of overlap as well, these diagonal plots, not much separability at all. And same goes with the what you call it, the scatter plots. So let's move on. And here is my data processing. I'm looking at 10 components, PCA components, but I'll get to that in a second. Here, this function just splits the test and scales it. And we're looking at, this is our target feature, which is condition. So I chose to kept 10 principal components. It's like I said earlier, we took out the target label. Still 22 feature components. I mean PCA components that it creates. 5 components only explain about 50% of the variance, which is very low. And I chose to keep 10 because it explains about 77% of the variance, which I think it's much better than 20 and than 50% because you're leaving a lot of information off the table there. So 77%, pretty good. So let's move on here and create a histograph of my PCA components that I just created there, the 10 components I decided to keep. So here it is. first thing I really want to mention is that 8 out of the 10 PCA components I decided to keep, well, many of them have a nice, somewhat normal distribution, um, which I think will come really in handy for like models such as the Gaussian NB. It does really well on data that are features that have a somewhat normal distribution. Even though these first two explain most of the variance, um, having 8 out of the 10 having a somewhat of a normal distribution, it will, I think, really help the Gaussian NB find some nice generalized patterns. So now on to the first two components. Um, these two probably have, this one has the most separability out of all the PC components. So, for our disease here, the peaks are nicely distinguished. Some overlap right somewhere in the middle, so that will help the models such as like SVC find nice can work on these kinds of data as opposed to the you know these other components. Same thing goes for this one. Still a lot of overlap. The peaks are nicely distinguished. Heavy overlap, but I think SVC can do something with this. Find some nice decision boundaries for these two components. But overall, yeah, just to kind of here's my pair plots, all my components. So kind of getting a closer look here. There's still really a lot of overlapping when you just look at the diagonal plots here. So we have a nice, distribution. Uh, Again, separability, nice separability, more so for PC1. So I think, but if we take a look at the scatter plot for these, compared to the original before the PC components, there wasn't much separability at all. But for PC1, there's kind of a nice little, a little less overlap, but still, quite a bit. But most of them, so pretty nice. It's very, very a lot of overlapping. So models like logistic regression, and I think the decision tree, I think we'll have a hard time finding those finding a generalized pattern from these things, from this data set. So yeah, here's my retuning. This is my base model. So far, these models did a pretty good job. I'm not gonna spend too much time on these results, but so far, KNN did a pretty good job. SVC did a lot of better job. I do want to flag that for SVC, its recall able to for class 1 is very low compared to KNN there, which is a major red flag. And then Gaussian, as I predicted, did a really good job. It has a really high precision for class 1, 86% for class 0, and a pretty high recall score there. Decision tree, yeah, just as I was saying earlier, since this is an unbounded tree, it's the default there. It's trying to find these really complex decision boundaries, so it's not doing a really good job there at all compared to the other models. This one surprised me. It did a lot better than I would expected. So there's not a lot of like brain farted there. A little had a brain fart. Um, so as I was just saying, so logistic. This one really surprised me because again, there isn't much of a considerable like separability for logistic regression to create that decision boundary. Um, in my data here, so very surprising the results there. So yeah. Mm. So moving on to the optimized parameters. So here are my so KNN versus the default there. It picked 19 neighbors as opposed to the default of one. At a KNN F1 score of F1 of 8.15, and these look pretty good. We'll compare those later. And SVC has classifiers of a C value of 0.1. That means like it's pretty strict, and a linear kernel. So I thought it would have picked something a little thing like RBF, but yeah, linear. I'm very surprised with that. And here, decision tree, as I was saying earlier, the default is none, so it's an unbounded tree. So for it to pick two in a min leaf of 8, it's yeah, that's not a very complex decision boundary at all. And logistic regression here, the default didn't change at all, and yeah, but it had an F1 score of 8.23. In the newbie, in the Gaussian NB, very small number. It's VR smoothing. It's very small. So yeah, let's move on. So since so again, I only for these metrics, I only kind of want to look at how well the model does at classifying um, those with the class one specifically because uh, if a model with a really low recall is gonna have it's that's a really bad sign, especially for detecting something like heart disease. So recall here is really the most important um, metric that I'm going off of. And so, you know, low percentage of false negatives is a very good thing. And it looks like model here did much. It did nominally better. It it went from 8.57 to 8.9. All around here, everything it did a little bit better, slightly better after pre-tuning. So instead of using just one neighbor, it looked at 19 neighbors. So it helped it kind of give it a more information when making its decision. But for class 0, nothing really changed at all. It had the same scores there. For SVC, here it also did a little bit better by giving its parameter linear classifier of C. I think it laxed. I think the default was 0.01 as opposed to, so by giving it kind of like making it a little more loose, it was able to do a little bit better for the recall, but everything else still very nothing changed on everything else there. So slightly better. His precision's really good, which is really surprised with that. 0.97, 0.93 again. The decision tree classifier did much, much better as opposed to its base model there, base parameters. As you can see here, this one gained the most from tuning parameters. So instead of having an unbounded tree, giving kind of having a not a very complex decision boundary, increased its recall. Yeah, went from having flagging from making 9 false negatives, it went down to 3. So that's a great increase. However, its false positive went up by 2 points, but 2 predictions. So I'm not too worried about that because again, I'm really more focused on its ability to recall on class 1 there. And for logistic regression, nothing changed at all. I mean, it changed the default parameter it chose wasn't really didn't change the default there. Same thing with the Gaussian NV, nothing changed. So which tells me that these kind of hit a capacity limit in terms of what the model can do with the data. So in the future, maybe because I'm working off of 5 models right now, I might pick different parameters to pick a type to optimize. Right now, I'm just optimizing for one. I have a lot more parameters, so just in the future, I would focus more on one model and tuning for that, and specifically for these two. See if I can get a better score, and just to make sure that it's doesn't hit its limit, capacity limit. For now, yet. So here, when we look at the F1 mean, the F1 standard deviation in tests, pre-tuning versus post-tuning, looking at all of them here, so the standard deviation it's really small compared to the mean, meaning that models are nice and stabilized and doing a pretty good job at generalizing. the data set. There's not really any overfitting. However, the test F1 is higher than the mean, which could be a red flag, given there's such a large gap. But nothing that I would, um, I'm gonna look into for now. Maybe later. I'm gonna look into this later. But overall, it's not underfitting. It's not overfitting. So yeah, it's doing an okay job at generalizing the data. Here's a graph of that table. So again, the hyperparameter tuning did a little bit, did you know made everything slightly better, except for the decision class tree, which gained a lot from tuning as hyperparameters. Yeah, and for the model that I would pick, it would be the KNN, due to its high accuracy score, the precision, the recall, the F1 over the decision tree, which has lower metrics there. Same recall score, but KNN KNN model here is much more reliable. Uh, yeah, overall, I think that's it. Um,